Welcome to phyloseminar.org, a project supported by the Society of Systematic Biologists. Let me remind you that there's a Q&A feature of Hangouts on Air, and I encourage you to use it. Today is the last talk in a series of 3 talks on ancestral recombination graphs. First, we heard Matt Rasmussen, then we heard from Peter Ralph, and today we're going to hear from Matthias Steinrücken, speaking from his new position at UMass Amherst. Matthias got his diploma from Bielefeld University while working with Ellen Backe, working on recombination dynamics with selection, then his PhD at TU Berlin with Jochen Blath, working on multiple merger coalescence. He then did a postdoc with Yun Song at UC Berkeley, mostly working on things that I think he's going to be talking about today. So welcome, Matthias, and I'm looking forward to your talk.
Hello, everybody. Thanks for the nice introduction. Let me just set this up. And get started. Just give me a second here. Okay, yeah. Again, thanks for the introduction, Eric. Thanks for having me here. As you said, I will actually be talking about some of the work, or most of the work, a large chunk of the work I did with Yun in Berkeley, and together with one of his PhD students, John Kem. And my presentation is entitled Demography-aware conditional sampling distribution for inferring ancient demography and detecting introgression pattern. And that's a lot of words, but I hope by the end it will be a bit clearer what I mean by this. So let me dive right in and start with talking about what I mean with inferring ancient demography, or when I say ancient demography, what do I mean by this? So I have put on the slide this picture from Hennedal in 2012, but there's like a lot of these pictures around, which kind of summarizes our understanding, our current knowledge about how modern humans populated the world. There was they originated, I don't know if you can see my cursor, in Africa around 100 years ago, and then migrated out of Africa, and through a series of migration events and bottleneck events, they populated the Earth, and now they are living in more or less every place there is. Why is it interesting? Why are people concerned with this ancient demography? The reason for that is that this whole, these migration events, this population size changes, these bottlenecks, they leave traces in the genetic data. And these traces in the genetic data can confound analysis that you want to do with this modern genetic data. So for example, if you want to do association studies, you can be confuse your patterns that are due to demography and can wrongly assume that they're actually association with disease traits, but in fact they're just effects of the underlying demography. If you want to look for regions in the genome that are under selection, it is also known that patterns of demographic histories can lead to the same pattern in the genetic data that selection does. So in order to look for selection, you have to kind of know the underlying demography to not be confused by that as well. There's also room to improve admixture mapping, or just sometimes people just want to know about this demographic history for historical interest. So people just want to know when did certain populations migrate from where to where and how are they related to each other. So that's also a good reason why you would be interested in ancient demography, and you would be willing to, you would want to infer it. So as I said, this is it's a very, very interesting topic, and it has a number of applications, and a lot of people are interested in and have been working on this for kind of as long as population genomics is around, and even longer. And here I just listed a few of the more recent methods of people that use population genetic methods to address these questions of how does the ancient demography look like. So the first item on my list is the so-called, or what I call the frequency spectrum-based methods, which one of the more widely known proponents of this method is this method DADI, developed by Gutenkunst et al. These methods, just by their nature, can be applied to very large sample sizes. However, also just by their nature, they completely ignore linkage information along the chromosome, along the genome, which is known to be informative about demographic history. So thus there are, on the other end of the spectrum, there are these what I call full sequence-based approaches, like Lee and Durbin's PSMC that has received a lot of press, and the subsequent version MSMC, which tries to capture as much of the linkage information as possible. However, this comes at a computational cost, and thus these methods are usually only applicable to small sample sizes. And then somewhere in between, there are methods that use the information from tracts of shared ancestry. What I mean by that is that if you look at the genetic data, you see that between individuals, certain tracts on the genome are shared, have a shared ancestry. And if you tabulate all these shared ancestry tracts, you ask yourself, how many tracts do I see of a certain length? And you look at this spectrum, at this distribution. You can actually also relate the distribution of this length spectrum to the demographic history, and thus do inference about demographic histories based on this this spectrum of shared ancestry tracts. And this includes some more linkage when compared to the frequency spectrum-based method, but it doesn't include quite as much linkage as the full sequence-based methods. And thus, they are somewhere in between. They include some linkage and can be applied to moderate sample sizes. And yeah, some recent works in that area is by Palamara et al. Or Harris and Nielsen. So I basically want to add my method to the list as well today. Our method called decal, which I will present today, can be used to infer parameters of general demographic models from multiple sequences. By general demographic model, I mean really general models. You can have an arbitrary number of subpopulations, changing population sizes, variable migration rates, continuous migration, pulse migration for mixture events, times of population divergence, population split, basically a lot of things in everything you can think a demography can have. Some of the extension I just want to mention at this point that we are kind of working on is one of them is to include samples from different times, so not only genetic samples, genome sequences sequenced at present, but in the last years, this ancient DNA, a lot of people have started to collect DNA samples from ancient remains, and we are working on incorporating such information into our method. Our method also kind of naturally allows to incorporate quality scores and missing data in a principled way. The missing data we actually do incorporate, the quality scores we haven't quite done yet. And another thing we're working on is to make our method work better with diploid individuals, because although people promised us that several times, nowadays experimentally phased genomes are still very rare, and you have to just deal with the fact that you don't have phase information in your data nowadays. So this is basically the demographic inference part of our method, but after I present you the model, I will also show you some examples that show that the underlying model can actually be used not only for demographic inference, but for just a number of other questions of population genetics have, like mixture deconvolution, posterior distribution on ancient haplotypes, detecting incomplete lineage sorting, detection of identity by descent, phasing and imputation, all of that accounting for the underlying demography, inferring marginal genealogies, and everything you can basically think of yourself after you've seen the model. So with this, let me now start actually introducing our model, or even a step back, introducing some background that I think you need to better understand the model and to motivate why we do certain things. And of course, a talk in a series about ancestral recombination graphs. The first slide in the background section should start with the ancestral recombination graph, so that's what I do. In the other talks, we actually had already nice introduction to the ancestral recombination graphs, but I just want to go briefly through it again and point out some of the things I think are important to understand our method better. So basically, the ancestral recombination graph is a data structure that captures the genealogical relationship between a set of sequences. Sometimes I call them haplotype as well. And it includes ancestral recombination, coalescent, and mutation events, all in this one data structure, everything that relates this sample, the set of sequences. And there exists a generative model that's widely used, the so-called coalescent with recombination, that's used to generate ancestral recombination graphs, and also in a second step, actually used to generate sequence data. So you can use this coalescent with recombination to simulate sequence data. And this happens as follows. So in this example, I'm looking at 3 sequences. Each of them has 3 loci, and I want to know, I want to just generate a genealogy relating these individuals and generate genetic data for these individuals. So what I do is the following. Under the coalescent with recombination, I start an ancestral lineage for each of the haplotypes at the present, and they extend into the past. While they are extending into the past, they can, at certain rates, certain events can occur. For once, they can coalesce. If 2 ancestral lineages find a common ancestor at some point, then the ancestral lineages coalesce. Another thing that can happen is recombination. In this example, recombination between the first 2 loci and the 3rd locus. And then in the ancestral recombination graph, this is modeled as the ancestral lineage branching into 2 separate branches, one for the left part of the sequence, one for the right part of the sequence. And then these ancestral lineages evolve back into time, coalescing, and ultimately you can show that they will all have coalesced into one single most recent common ancestor. And then in order to, so this generates the ancestral recombination graph, and then in order to generate sequence data for the individual I sample at present, I sample sequence data for the most recent common ancestor from the stationary distribution, and then I propagate the alleles through the arc to the present, accounting for the fact that mutation, which happens at a certain rate, can alter some of the alleles on the way from the ancestor to the present individual. So yeah, so this is basically in a nutshell how the arc can be used to simulate sequence data. And just one thing I want to point out here, which will become important later, is that if you look at this data structure, the ancestral recombination graph, in more detail, you see that at each locus, the individuals are related by a tree. So if I look at the first locus and traverse this ancestral recombination graph, traverse the ancestry for the first locus, this is the part that I highlighted in red here. So with the recombination event, I have to follow the branch for the left part of the sequence because I'm in the left part of the sequence. And I see that this red thing is a tree embedded in the ancestral recombination graph. On the second locus, it's the same tree because I have to traverse this recombination event exactly the same way. However, if I then go to the third locus, I see that actually this tree changes and the individuals are related, or on the third locus, the individuals are related by a different tree that's obtained by traversing the ancestral recombination graph in a different way. So another thing that I wanted to note now is what I already kind of said, that ancestral recombination event changes the local tree. So if I look along the sequence, if I look along the sequence, the individuals are related by a tree. But whenever I encounter an ancestral recombination event as I go along the sequence, this local tree changes. Yeah, and this is basically one of the features that will become important later. But for now, I've shown you this, shown you how to generate an ancestral recombination graph. And implicitly in this picture, I assumed that that there was a single underlying population, a panmictic population of a constant size. However, when I want to infer something about demography, I have to think about how demography actually enters this picture. So I have to think about how a demography affects the dynamics of the ancestral lineages in the coalescent with recombination. And this happens in the following way. So here I've put an example demography on the slide, which is just an ancestral population that splits into two. One of the subpopulations has a bottleneck event. The other subpopulation splits again into two. There's some G-flow after the divergence event, but at the present we have three isolated subpopulations. And now if I think about a sample of sequences taken in these three subpopulations, how does this demography influence the dynamics of the ancestral lineages of this sample? I would say this can be best shown in three ways. So the demography influences the dynamics in three major ways. The first is lineage from the isolated lineages from isolated subpopulations cannot coalesce. And I try to depict this here between the first and the second subpopulation. They are isolated, so ancestral lineages cannot coalesce, which is kind of clear because ancestors cannot meet each other because they're an isolated subpopulation. However, the second point, if migration is possible, then ancestral lineages can actually change between subpopulations, which is just, yeah, if individuals can migrate, then you can see how ancestral lineages can go from one subpopulation into the other. And the third thing is that coalescence of ancestral lineages happens at a slow rate in large populations and at a fast rate in small populations. And I try to visualize this a bit here in the first population, where only one coalescent event happens in all this time and during this huge, when the population is large. But in this bottleneck, there's a short sequence of two coalescent events. And the intuitive idea behind that is that in large populations, coalescence is slow because in large population, there are a lot of individuals, a lot of potential ancestors around, and so the ancestral lineages just take a long time to meet by chance. Whereas in small population, there's just less ancestors around, less individuals, the group is smaller, so just by chance, the ancestral lineages meet quicker. So all in all, I've shown you how this generative process, the coalescent with recombination, can be used to generate samples of sequences, and shown you how demography affects this, the dynamics of the ancestral lineages in this model, the generation of sequences. So then what I can do if I want to infer something about the ancient demography, I can say, okay, let me parameterize the demography by theta and say I want to compute the probability of observing a certain set of haplotypes, my observed data, under the coalescent with recombination and a given demography by theta. And then just in a maximum likelihood fashion, I can say, using this probability, I find the demographic parameter that maximizes this likelihood, and then I report these as my maximum likelihood estimate for the demographic parameters. The inconvenient truth is that, unfortunately, it's not that easy because there's no tractable way to compute this likelihood. The state space of ancestral recombination graphs is just large, and Matt Rasmussen has actually shown a nice way to try to navigate this state space, but it is very large, and just integrating over all possible arcs relating a sample is just not feasible. And thus what I want to do today is I want to approximate this likelihood in a composite likelihood framework using the so-called conditional sampling distribution. And this conditional sampling distribution is basically, instead of asking for the likelihood of the whole sample at once, I'm just asking, if I have already observed a bunch of sequences, what is the distribution of an additional sequence that I observe? So basically the conditional sampling distribution is the probability of observing an additional haplotype Hn after having already observed haplotype Hn through Hn-1. And by this subscript theta, I want to emphasize that this conditional sampling distribution is aware of the demography, so it accounts for the underlying demography, which, as I've shown you before, influences the dynamic of the ancestral lineages. So now I first want to show you what we do to compute this conditional sampling distribution, and then afterwards I'll go back and tell you a bit about how we use it in a composite likelihood framework to infer something about the demographic parameters. So on this slide is basically again the question of the conditional sampling distribution visualized in a graphical way. So we have given observed haplotypes, in this example H1, H2, H3, and an underlying demography, in this example just an ancestral population that splits into two with subsequent migration, which stops at some point, and then at the present we have two isolated subpopulations. Now the question of the conditional sampling distribution is how to sample an additional haplotype called alpha in this example. What is the distribution of the alleles at the loci of this additional haplotype? How do I describe this distribution? Or later, how would I compute the probability of observing a specific haplotype? What I would like to do is the following. If I would know the ancestral recombination graph that relates the sequences that I already observed, I could kind of figure out how I have to hook in the ancestral lineage of the additional haplotype into this already existing ancestral recombination graph, and could describe the distribution of the additional haplotype in that way. However, the problem is I don't know this ancestral recombination graph. And again, Matt in his talk actually showed a very nice approach to trying to get at this ancestral recombination graph relating a set of sequences. However, in this method, we took a different approach, which sounds very crude at first, but it actually works. What we assume is that actually, not knowing the recombination graph, we just assume that the ancestral lineage of each of the already observed haplotypes extends infinitely into the past and doesn't undergo changes. They don't recombine, they don't mutate, they don't coalesce, nothing. They just exist forever into the past. And then in order to describe the distribution of the additional haplotype, and I will first take the approach as describing this as a generative process, and later we will see how to use it to compute probabilities. To describe the distribution of the additional sampled haplotype, I will proceed locus by locus. And in order to describe the alleles of the additional haplotype, the allelic distribution, I will first specify a marginal additional lineage at each locus. And I go about as follows. I start at the first locus and say, okay, at the first locus, I start an ancestral lineage that it extends into the past and undergoes the dynamics according to the demography. So whenever migration is allowed, it can migrate between subpopulation, and it is ultimately absorbed, it ultimately coalesces with one of the lineages from the trunk haplotypes in the population it currently resides in, at a rate inversely proportional to the size of this population. And so that way I account for the 3 points that I mentioned, how a demography influences the dynamic of an ancestral lineage. Migration where possible, isolation where no migration is possible, and coalescence is fast in small population and slow in large populations. And if I choose to be absorbed in a population, the haplotype, the specific haplotype is actually chosen uniformly amongst the haplotypes in the population where I choose to be absorbed. So this is how I can sample a marginal addition in a genealogy at the first locus. And then I proceed along the sequence. I go to the next locus. And as I go to the next locus, remember what I told you when I introduced the ancestral recombination graph. If two loci are not separated by an ancestral recombination event, then the marginal tree at the two loci is the same. So if there's no recombination event, then I just copy the marginal from the marginal lineage from the previous locus to the next locus. However, if there is a recombination event, it happens at a certain place with a certain distribution. So in this example, let's say it happened where this red cross is. Then what I do is as follows. I copy the marginal additional lineage up to the recombination breakpoint to the next locus. And then after this recombination breakpoint, I break the lineage off and I allow it to independently undergo the marginal migration dynamics independently of everything that happened before. And thus it starts extending into the past, migrating around, being ultimately absorbed into a potential different haplotype at a different time. Yeah, so this procedure can be used to sample a sequence of marginal genealogies for the additional haplotype. And now to actually describe the alleles, or to describe the allelic distribution of the additional haplotype, I do the following thing, very similar to the ancestral recombination graph. I copy the allele of the observing haplotypes at the respective locus at the time of absorption and propagate them to the present. Again, accounting for the fact that mutation happening at a certain rate might change the allele along the way. And then I have finally sampled an additional haplotype. This basically describes a generative process of how to sample an additional haplotype. One thing I want to mention at this point, the assumptions of this are very similar to the SMC. What I mean by that is that in the ancestral recombination graph, there are under the coalescent with recombination, there are long-range dependencies between loci. So what happens at a given loci can actually be affected by what happens 1 kb down the line. However, people have realized that if you ignore these long-range correlations, then you lose very little accuracy, but you gain a lot in computational efficiency. And that's what people have termed the SMC, the sequentially Markovian coalescent, which refers to this effect of ignoring the long-range dependencies for the sake of computational efficiency. And yeah, basically, by just traversing this additional haplotype in a Markovian fashion, I'm kind of doing the same thing. Yeah, so this is the generative model, but just if you realize, if you see that this as a hidden Markov model, where the marginal additional lineage is the hidden state and the observation is the allele at a given locus for the additional haplotype, you can actually also use this generative model to compute probabilities. Probabilities for a certain observation for a certain additional haplotype. And this hidden state space, the marginal additional lineage, is actually still quite complicated. It's for starters continuous, but also there's some other aspects. So we do, in order to get an efficient implementation that computes the conditional sampling probability of an additional haplotype, we do have to do some more tricks, including discretizing the absorption time, but in the end, we have developed an efficient implementation of this hidden Markov model. And one thing I wanted to mention at this point, as I said in the beginning, this approximation of each trunk lineage actually being unchanging, existing for an infinite amount of time, is a bit crude, and indeed it doesn't work too well. But you can, we did some modifications to this assumptions to make this more sensible, and then you can, yeah, and then it actually turns out that you get better estimates if you model this trunk a bit more appropriately. So yeah, this conditional sampling distribution implemented in an efficient hidden Markov model framework can then be used to compute the conditional sampling probability. And then I use this conditional sampling probability in the following composite likelihood framework to get an approximation on the likelihood. So actually, instead of asking for the probability of the whole data at once, what I'm doing is I actually construct the sample sequentially. I start by first sampling the first haplotype, then sampling the second haplotype based on the given the first, then sampling the third haplotype given the first two, and so on until I've constructed the whole sample sequentially. And yeah, I just showed you our version of this approximate conditional sampling distribution. So if we do this, we actually don't get the likelihood. We get an approximate likelihood. However, if we would be able to compute the correct conditional sampling distribution, one can actually show that this sequential construction of the sample is actually equivalent to the likelihood. It is equal to the likelihood, and thus constructing the sample sequentially is equivalent to just taking the sample at once under the true conditional sampling distribution. But as I said, we cannot get the true conditional sampling distribution. We only have an approximation, so we only get an approximate likelihood, or an approximation to the likelihood. Another thing that happens is, if you have the true conditional sampling distribution, the order in which you construct your sample doesn't actually matter. It doesn't matter which is the first haplotype and which is the second haplotype. However, under the approximation, the order does matter, but in order to mediate that, we take an approach that was already introduced by Lee and Stevens in 2003, the product of approximate conditional, which averages over several random orderings of the haplotypes, and thus mediating this effect, and the order matters less. And it turns out that actually this works in practice pretty well. So then, all in all, what we can do, and what we do in our method, which we call decal, demographic inference using composite approximate likelihood, we use this approximate likelihood defined in this way based on the conditional sampling distributions in an expectation maximization framework to find a maximum likelihood estimate of the demographic parameters. And it's all only approximate because we only have an approximate likelihood. But this estimate turns out to be actually pretty good. And one thing I wanted to say before I show you some examples of this method in action. This is actually related to the method PSMC by Lee and Durbin. Lee and Durbin basically estimated ancient population sizes in a single population from a sample of 2 sequences. And if we take the special case of our model of a single population and a sample of 2 sequences, these models are basically the same. Yeah, so with that, let me just go into some examples. So one example I wanted to show you, which has been already published in this genetics paper by Yun Song and Sarah and Kelly, 2 of his PhD students. They looked at the special case of this method of a single population with varying sizes. And what they did is in this particular example, they simulated some true population size history, here the red dashed line, and then they used, on the one hand, PSMC, and on the other hand, decal, our method, to estimate this population size history from the data. And what you see is that they actually do both pretty well in the more ancient times. However, in the more recent times, decal does substantially better. And this is due to the effect, the well-known effect that if you want to get at events that happen in the very recent past, you need larger sample sizes. And as PSMC can only use 2 samples, the resolution in the recent time is not that great. However, decal, you can add additional samples, and you can get a better resolution in the more recent times. So another example I looked at, kind of demonstrating the ability to incorporate multiple population, is this population model of a clean split, where we have an ancestral population of a given size. Then there's a strong bottleneck. After the bottleneck, the population splits into 2, and at present we have 2 extant populations of given sizes. And yeah, these bottleneck event and the split happens at certain times. Just don't think too much about the exact numbers. It's just some numbers that I encountered at some point. Just for the sake of this example, I fixed these numbers to these values, simulated a data set with 2 haplotypes per population, each 150 megabases, and then I used our method. Our method can, on the one hand, be used in the expectation maximization framework to estimate demographic parameters, but we can also use it to just calculate the likelihood, the approximate likelihood under our model. And so this is what I did here. For this picture, I fixed the ancestral population size, the time the bottleneck starts, and the 2 extant population sizes. So the only 3 parameters are the divergence time, TD, and the size of the bottleneck, NV. And then I computed the likelihood on a grid, on a 2-dimensional grid for these 2 values. And you see that actually the likelihood surfeit has a nice maximum, and the maximum is actually pretty close to what the true parameters in the simulations were. And to give this a bit more, make this a bit more quantitative, not only looking at one example, but looking at a bunch of examples. So I repeated this 16 times. I simulated 16 such data sets and performed an expectation maximization to infer the demographic parameters. But this time I optimized over the whole 6-dimensional parameter space. And for each of the 16 replicates, I plotted the reported maximum likelihood estimate. And what you see, or actually what I reported, is the base 2 logarithm of the maximum likelihood estimate divided by the true value. So this quantity would be 0 if the estimate would be exactly equal to the truth. It would be 2 if the estimate is twofold overestimated, or -1 if it's twofold underestimated. And we see that basically the times are actually spot on. The extant population sizes are a bit more shaky, which is again due to the fact that I mentioned earlier that to get a good resolution for more recent times, you need more samples. Yeah, and the population sizes, the ancestral size is pretty good. There's a slight bias in the bottleneck size, but in general, this performs pretty well. And so I wanted to also show you another example where I looked at an isolation with migration model, where we have an ancestral population of a given size that splits into 2 at some point in the past, and then there's these 2 sizes, but they exchange these 2 populations, but they exchange migrants after the divergence at a given migration rate. And this scenario is actually pretty hard to get at, because you can imagine that easily if you increase the migration rate and at the same time decrease the divergence time, the genetic data looks very similar. So it's really hard to distinguish between strong migration or early divergence in this model. But I tried with our method anyways. I fixed the population sizes and computed a 2-dimensional likelihood surface where I varied the divergence time on the x-axis and the migration rate on the y-axis. And what we see is that we actually get a nice maximum in our surface. Unfortunately, the maximum is just a little bit off. But I would say, if you regard that the divergence times and the migration rate is actually pretty intertwined, this is actually a pretty decent estimate, which which can be certainly be improved on in the future. And just what I mentioned earlier, that you can easily imagine of sacrificing a larger migration rate for an earlier divergence time. You can see this kind of in this picture of the likelihood surface as well, in this banana shape, because you can either say, if I don't allow migration, then I get a very recent divergence time. However, the more migration I allow, the more the later the divergence, or the more ancient the divergence is. But our method actually does a fairly decent job at actually pinning down a maximum in this space as well. So with this, I want to mention a few things about the runtime. Just the more theoretical part, the conditional sampling distribution is, as it is a hidden Markov model along the sequence, it's linear in the number of loci. We have to consider each trunk haplotype for absorption, so it's linear in the number of trunk haplotypes. If we use this PEG framework for estimation, we get another factor of number of haplotypes, so the estimation is quadratic in the number of haplotypes. And just to give you some concrete number, the average runtime per expectation maximization on the simulated data sets I just showed you before for the clean split model, that meant for haplotypes, 150 megabase per 6-parameter optimization took on average 7 hours. Admittedly on 16 cores, but everybody has 16 cores at home, right? Yeah, so I hope this convinces you that our method can indeed be used to accurately and efficiently estimate demographic parameters of interest. So with this, I want to, actually one more thing. I wanted to show you this one example that we did once, where we actually looked at some data from the 1000 Genomes project. We extracted the data for 20 haplotypes from the CEU and from the urban population, a 2 megabase per sequence, and tried to estimate the divergence time in a clean split model and compared it to some other estimate that were reported in the paper, in the DADI paper. And we actually see that we get way narrower confidence intervals, and in the dash, so the solid lines are the borders of the confidence intervals, and the dashed lines are the point estimates. So yeah, again, I hope I have convinced you that our method can be used to efficiently and accurately infer demographic parameter of interest. And then let me get to what I actually alluded to earlier, is that the underlying model, the conditional sampling distribution, can not only be used for demographic inference, but for a number of other population genetic, to answer a number of other population genetic questions as well. So one of the examples I wanted to show you is to detect local ancestry in mixed populations. To just briefly, what does it mean to have an mixed population? Basically, we have the scenario is as follows. We have an ancestral population that splits into two populations. Both of them evolve are isolated from each other and evolve independently. An example would be African and European population. And then recently migrants from both of the populations come together in a different place and start mixing. So for example, the African and European start mixing in North America. And then if you look at the genome of an individual in this mixed population, what you see is the following. If you think again about the ancestral recombination graph, I told you as you go along the sequence, when you encounter recombination events, the local ancestry, the local tree changes at these recombination events. In this scenario, that means that if in one part of the genome your ancestor for this part of the genome actually came from the red population, as you go along the sequence, a recombination event might change this ancestral state, that at another point of at another position in your genome, your ancestor actually comes from the blue population. And so if you look at the genome of an mixed individual, it's basically an alternating sequence of regions of red ancestry alternating with regions of blue ancestry. And we can use our CSD to detect these segments in the following way. We basically just say, okay, the individuals from population blue and population red are this unchanging trunk. We put the mixed individual as the additional individual, as the additionally sampled haplotype. And then using the posterior decoding in the hidden Markov model, we can actually get posterior probabilities at each locus on the posterior probabilities on the absorbing haplotypes, and thus effectively posterior probabilities of the most likely ancestry at a given locus. So thus we can use our CSD in that way to detect these tracts of local ancestry. And just an example to show you how this works. Here I have some simulated data under such a mixture scenario. In this case, the 3 haplotypes I simulated were mostly of red ancestry. However, there were some segments of blue ancestry in these haplotypes, and then we can use our conditional sampling distribution, as I just described, to try to detect these tracts. And you see in this picture that we're actually doing reasonably well. Or in a more quantitative way, we can assess this by doing a bunch of simulation and plotting a ROC curve, plotting the true positive rate versus the false positive rate. And this is actually not the full ROC curve, it's only the upper 0.05 in the true positive rate and the lower 0.05 in the false positive rate. So we're actually doing very, very well in detecting these local ancestry tracts. And just as an example, I've also try to detect these ancestry tracks using a software called RFMix, and we're actually outperforming this software. So we're actually doing pretty well to detect these local ancestry tracks. And going to a slightly different application, but in principle it's very much the same underlying phenomenon. And people have been working on that as well, as what I entitled Introgress Tracks of Neanderthal Ancestry. So just briefly some background on the setup for this. People have been gathering in the last years increasingly high quality genetic data for ancient hominins. Just an example, this paper by Prufa et al., where they presented a high quality sequence for a Neanderthal individual. And the availability of this high quality ancient genetic data actually helps to shed light on the demographic history that relates modern humans and these ancient hominins. And basically what people have figured out by looking at these Neanderthal sequences, that our relation to the Neanderthal is basically something like this, where there is an ancestral population that splits into Neanderthal and modern humans at some 300,000 years in the past. Then the modern humans split into African and Europeans some 60,000 years ago. Shortly after that, there was some admixture event where some migrants from Neanderthal came into the European population, and this is believed to be a 2 to 3% admixture event. Actually, it's kind of wrong to say Neanderthals came into European. It's more like Europeans came out of Africa into Europe and found Neanderthal already being there. And then they admixed a bit, but ultimately Europeans took over and Neanderthals became extinct. But in principle, the same thing that happened before, what I described before in the admixture scenario, applies here as well. If you look at the sequence of a European individual, at each locus, the genetic material can either be more closely related, if the ancestor stayed in the European population all the time, and coalesces ultimately with a lineage of the African population, it's more closely related to the African genetic variability, whereas if the ancestor to this segment of the sequence came from the Neanderthal population through this migration event, then it will more likely have coalesced with the Neanderthal lineages first, and then thus it's genetically more closely related to Neanderthal. And then again, as you go along the chromosome, ancestral recombination event can change this ancestry state. So if we look at it in simulated data, and I paint African ancestry blue, Neanderthal ancestry red, you see if we do some simulation under some model with reasonable parameters, the parameters that I showed you before, we get that most of a European chromosome is more closely related to African. However, there are these small, short fragments in there that are more closely related to Neanderthal. And the whole problem of detecting introgress tracks of Neanderthal ancestry is now to determine where these regions are. And again, we can use our conditional sampling distribution in the same way as before. We say the Neanderthal and the African individuals, we put them in the trunk, and we use the European individual as the additional sampled haplotype. And then just using the posterior decoding of the hidden Markov model, we can at each locus figure out the most likely ancestry state, And if I plot the marginal posterior distribution that our conditional sampling distributions gives us in this picture, you see that this actually works fairly well. Mostly it says that the individual is of African ancestry. However, you see that it picks up on these short regions of Neanderthal ancestry. Again, we can do this in a bit more quantitative way and simulate a lot of data and plot ROC curves and precision recall curves and convince ourselves that we are actually pretty well at finding these ancestry tracks in simulated data. And if we compare this to some method that was put forth about a year ago by Shankararaman et al., and if we compare the method on the simulated data, we see that we actually outperform their method as well. However, we did use, for this analysis, we did use the same parameters for the analysis that we used for simulating the data, so that might be a bit unfair. However, we also looked at what happens when we misspecify some of the parameters in the analysis. But basically, the performance doesn't drop by too much. We are still doing pretty well, even if you're uncertain about some of the underlying parameters. So now that we have convinced ourselves on the simulations that we are actually reasonably well equipped to do this, we also looked at some real data. So the data set we looked at consisted of all the European haplotypes in the 1,000 genome data and all the European haplotypes in the 1,000 genome data. And furthermore, the high coverage Altai Neanderthal sequence that was presented in this paper by Pruifa et al. And what we then did with this data set, we took each CEU haplotype in turn, put the Yoruban and the Neanderthal into the trunk, and then try to estimate or try to detect these Neanderthal ancestry in each European haplotype. And then we can summarize the results in a plot like this. I apologize if the labels on the axis are a bit small, but basically this is chromosome 2, and at each of the 250 loci, 250 megabases, we see what we plotted is an average over the European, so the average propensity of a European to have Neanderthal ancestry in that given window. And we see that there are positions in the genome where Europeans are more likely to have Neanderthal ancestry, and other regions where it's actually not very likely to have Neanderthal ancestry. And in this plot, in red, I plotted the posterior that was calculated by Shankararaman et al. Using their method, and in blue, I plotted the posterior calculated using our method. And as you see, they agree pretty well, although there are some slight differences at some places. And additional thing is plotted here in green. There was actually another paper last year by Wernet and Aki, which also aimed at detecting regions in the Europeans where they are more likely to have Neanderthal ancestry, and the regions they reported I indicated in green in this plot. So you see that there's actually very good concordance between all of the different methods in finding these Neanderthal tracks. Yeah, so then another way of summarizing the data is to just look at the average proportion of Neanderthal ancestry on each chromosome, sliced by chromosome. So we see that actually the two methods, our method and Shankararaman's methods, are actually pretty close. However, we on average find a bit less than they do. And this is kind of, can be summarized even more. On average, over the whole chromosome, over the whole genome, we find 0.93% Neanderthal introgressed tracts, whereas Shankararaman and al. Find 0.99%. In a Venn diagram that would look like this, so there's a huge overlap of 0.75%, but there are some regions that are found by one method but not found by the other method. And just looking at a slightly better resolution at this problem, what we plotted here is the absolute and the relative frequency of Neanderthal fragments of a certain length. So we detect these Neanderthal tracts and they have a certain length, and then we just look at how many fragments do we find of a given length. So this is the absolute number, here's the relative number, and in the relative number I actually added into the plot an expectation under neutrality. So if we would assume this demographic model I presented earlier and then just evolution of these tracts under neutrality, we would expect a distribution like this black one. and we see that maybe we are a bit more closer to the our distribution is a bit more closer to the one you would expect under neutrality. But what you can say for sure is that Sriram's Shankararaman et al.'s method finds a lot more longer fragments, whereas we find a lot more shorter fragments. And of course, we don't have any reason to believe that there would be neutrality. So the explanation that is put forth to explain this deviation from neutrality is selection. So one thing that Shankararaman et al. Already noted, and we find as well, is that there are so-called deserts. There are large regions in the European genome without Neanderthal ancestry. And we are currently investigating whether these regions are larger than you would expect by chance, but they seem to be. And Shankararaman et al. Argued in their paper that this is due to widespread negative selection against the Neanderthal introgression. So saying that in general, the modern humans that came out of Africa were actually already genetically pretty well equipped compared to Neanderthals, and the introgressed Neanderthal tracts on average were pushed out by selection because they couldn't compete with the human genetic variation, or with the modern human genetic variation. However, one thing they do note is that it seems that in certain skin and hair related genes, Neanderthal ancestry is enriched, and the story that they put forth for that is that although on average the modern humans out of Africa seem to have good genetic material, the Neanderthal that already lived in Europe for some time were already had their skin and their hair genes were already better adapted to the harsh European environment compared to Africa, and thus the Europeans basically took those genes from the Neanderthal and incorporated them because they were beneficial in the new environment. With this, I kind of want to conclude here. That's all I want to say today. In summary, I presented you our method to infer demographic parameters, which can be applied to multiple genomic sequences and to a wide range of demographic scenarios. I hope I've convinced you that it's accurate and efficient. I've also shown you some examples of how this conditional sampling distribution can be used to answer other population genetic questions. For example, detecting local ancestry, or in particular, detecting Neanderthal introgression. And just want to mention that decal 1.0, the inference of ancestral population sizes in a single population, is available at this SourceWatch project page. And soon we will add decal 2.0, where you can infer parameters in a very general demographic setting. With this, I want to just thank a few people. Foremost, Yun and Jack for working on this with me. Also Sarah and Kelly, who worked on this special case in the single permitted population. I want to mention Josh Paul, Emilia Witzorek, and Sriram Shankararaman, who helped me also a lot, the latter two in particular with the Neanderthal data, and also thank the rest of the song group for helpful discussions and some funding. So, and you for listening. Thank you very much.
Thank you very much. That was a very interesting talk. I just have a couple questions to get things started. So can you describe what modifications you are thinking about in terms of the trunk? I mean, so you have this model that everything persists back forever, and then you said that you had some modifications of that helped, but I was just curious what those were.
Yeah, basically the most important modification is saying that they actually don't exist forever, so that the number of ancestral lineages as you go back in time does decrease. So under this very crude first assumption, the number of ancestral lineages would always stay constant. But obviously that's wrong. So the most important change is to just allow this number of ancestral lineages to decrease. And another thing that also is important in this migration setting is to allow the trunk to migrate between subpopulations. So again, under the first approximation, we wouldn't allow the trunk lineages to migrate. Only the additional lineage would be allowed to migrate. And this is obviously not true. Obviously, the ancestral lineages of the already observed haplotype under the normal ancestral recombination graph model will migrate. So these are kind of two of the main.
I guess I still don't quite understand how you actually maybe implement that is the right word. I'm not sure. It just seems like you've got your HMM and it has like, you know, what the ancestry is the hidden state, and so are the hidden states changing as you go back, or what is it that's? I just don't see how. I mean, I understand that they would be nice to incorporate things. I just don't see how it would actually happen in the HMM framework.
Okay, so it's actually, I totally agree. I mean, I glanced over this, and there's actually a lot of details behind it. So basically, in our final implementation, the hidden state is at what time are you observed and into which haplotype.
I see.
And then one main thing to have to compute the transition probabilities of the Markov model is basically an absorption rate. You need an absorption rate in each population. And if you would assume this trunk where the number of ancestral lineages doesn't decrease, then this absorption rate would be the same at all points back in time, and it would be too high at all times. But since under the true model, the number of ancestral lineages as you go back in time will decrease, the absorption rate will also decrease. You will be absorbed at a lower rate back in time, which is basically saying that in the coalescence, like you coalesce less because there are less lineages to coalesce with around.
That's awesomely tricky. I like that.
And so basically the genetic variation of all the haplotypes does still exist, but the absorption rate becomes lower.
And is it's still uniform? Well, not uniform. Yeah, it's not uniform, obviously, but it's not as if certain lineages cease to exist. It's just
no. That's the thing exactly. The lineages don't cease to exist, and you're right. Which haplotype in a certain population I choose is still uniform, but basically the weight of each lineage becomes less, kind of.
Yeah, I like that. So I know that Sankaraman's method used a linear CRF, which a conditional random field, which is sort of more general than an HMM. But it's interesting that your method still performs better. What do you think is going on there?
So I mean, in principle, as far as I understood the method from Sankaraman et al., they still need to train their CRF on simulated data.
Yeah.
So they simulate data under this demographic model I presented, and then train their CRF based on this simulated data. And so basically, in our method, we include this demographic model, like it is part of the method, and in Sankaraman et al. Method, it's kind of also still in there. Like they don't explicitly include it, but through the training data set, this demographic model also comes into the whole picture. So yeah, actually I kind of, maybe let me start over. Another thing to mention is from talking to Sriram and his colleagues, it seems that their method has trouble detecting short fragments. And we seem to be a bit better at detecting short fragments.
Well, one thing I know that their CRF, it sort of has some really long-range averaging procedure where there's one contribution to the likelihood that's sort of like, how do things look for a good-sized chunk around where I am right now? So I guess that doesn't surprise me too much.
Yeah, that's another thing. Like this CRF is based on some features that they choose, right? And and I have to admit I don't have a very good intuitive explanation how these features relate to what we are doing. Like we're modeling kind of exactly what's happening, right? And we're not abstracting the data into features and then trying to work with the features. We're just working directly with the genetic data. And I don't have a good intuition of how really that relates. Just this empirical observation that apparently we seem to be better at picking up shorter fragments.
And so how are you going to incorporate the, I mean, I guess maybe what we heard about was actually decal 2.0 in a sense.
Yeah.
Okay.
The 2.0, the difference between this is basically 1.0 is a single population and 2.0 is an arbitrary number.
Cool.
So this whole migration and population split is kind of in 2.0.
And then after that?
Okay, I guess the diploid version might be 2.5. And I don't know yet what.
Let's see. So the diploid. So would you be doing phasing?
It would be very very similar to these. So these type of for example, I think Phase by Matthew Stevens uses kind of a conditional sampling distribution like model to do phasing, and it would be very similar to their model, basically using our demography-aware conditional sampling distribution in this phasing. So basically, you would instead of just sampling one additional haplotype, you would sample two additional haplotypes, and one way to sample two additional haplotypes is just to independently multiply two one haplotype models, which is the straightforward way which they choose. But you could account for some correlation within. If you sample two additional haplotypes, the lineages of the two additional haplotypes are not completely independent.
Yeah.
And there's some correlation between them, and you could, in the model that Matthew Stevens used, they didn't account for this correlation, but we thought about some way where you could maybe account for this correlation and thus hopefully achieve a better accuracy.
Cool. Well, it's all very interesting.
Thanks.
Well, it looks like that's it for my questions. Do you have a question, Wu? Okay. So. Thank you very much for your very clear and interesting talk.
Thank you. Thanks for inviting me.
Yeah, and good luck at Amherst.
Thank you very much.